And this is totally awkward, but let me remind you what we did 10 minutes ago with the Joule-Thomson. Here, I'm just going to write down the Joule-Thomson coefficient is, again, the Joule and Joule-Thomson are basically, there's this odd symmetry to it where you just replace the H's with the U's, or vice versa, the T's and the B's, and there you go. And again, you can see why it should actually be close to 0, but not quite. The Joule-Thomson here, let me give you some, because you can look these up. And I can tell you that these are actually very low numbers. Let's look at H2. Okay, H2 is a weird one. It's negative. Okay, now let's see. If it's negative, then, oh, that's a little Joule-Thomson. Okay, if it's negative, I got to remind myself what this is. It's dD dP at constant H. Okay, so if it's negative, if pressure goes up, temperature goes down. Okay, but the way refrigerators work, remember the way a refrigerator works, you should know this. I mean, probably as a kid you knew this. You have a pressurized gas being depressurized. Okay, so that makes that negative. And that would also have to be positive to be a negative. That means that if I have a refrigerator full of helium, hydrogen, it actually gets hot, right? So that would not be very useful unless you're trying to make a really weird heater. Helium is likewise negative. Again, confirming that hydrogen and helium are the weird ones. Air is 0.189. Now I want to point out again, remember I told you when is pressure dangerous? How many atmospheres? 2? Yeah, about 2. 2 is where cheap glass breaks. I'm largely a synthetic chemist, by the way. It's very unusual for a physical chemist. I'm largely a synthetic chemist. When I have a chemical reaction that's producing gas, and if it's enclosed, and it gets to 2 atmospheres, if that's cheap glass, it's already exploding. All right, and then my eyes are shredded. 2 atmospheres is kind of dangerous. And what kind of temperature? That'd be a temperature drop. If I built a refrigerator and it's 2 atmospheres, I get a 0.2 Celsius drop. That sucks, right? So these are small numbers. So you can imagine that you're going to have very high pressures, cycling that's continuous. Let's look at ammonium. Ammonia, okay, much greater. And freon, there's actually several types of freon, but one type I found is a bit better. Now seriously, ammonia is one of the best things that work in a refrigerator. There's a problem though. All right, when people figured out that they could, the huge thing about the Joule-Thomson thing was that people were able to make ice. Now before, 1880s, did any of you have any idea how people were, I grew up in Mobile, Alabama. Do you have any idea where we had ice? We still had ice in the 1800s. Where did we get it?
Canada?
Yes. They cut that stuff off Lake Erie and put it on a train. No fooling. They had no choice. They dragged it down from Canada. Because what the heck else are you gonna do? You got nothing else. You can't, oh, well, they had horses. How's a horse gonna make ice? Because that's all they had. Okay, so they start building refrigeration plants once they knew how, and they used the best fuel that they could get, which is ammonia, which is really explosive, especially when it's pressurized, and they tended to blow up, and then they killed a bunch of people. And that's why we went to freon, and then of course freon has its problems with the ozone layer, and now we have different fuels, but anyway. And have any of you ever seen the movie The Mosquito Coast? This is actually Harrison Ford's first movie after Star Wars. So he's like doing artsy stuff. It's about a guy who decides to leave it all. It takes his family, River Phoenix is in it, before he died. Oh, that's obvious. Anyway, so, what's that soldier? Universal Soldier, the one with the light. Anyway, never mind. Anyway, so now I really went off on a tangent. So Harrison Ford decides to leave it all. It's actually a really good movie, and yeah, it's old, so you can download it. And he goes to the Amazon rainforest, but what he does is he starts rebuilding his society. Because, he's uncomfortable, so he starts building machines, and then he builds a refrigeration plant and he makes it out of ammonia. And anyway, the movie ends very badly, by the way, so I just want to point that out. So anyway, yeah, that's where we get our refrigeration, and so I thought that was kind of neat. Now I also want to point out that if you recall, when we are ready to do the actual derivations for this stuff, so that right now with perfect gases this is 0, we're going to be doing it really soon. And again, like I say, I'm never quite sure if I really should be bringing this up yet. Remember that the compression factors versus pressure are equal to 1 for a perfect gas, but for things like hydrogen, they're above 1, and that's because they're very collision-oriented, right? They don't have very strong self-attraction, whereas other things like CO2 look like that. I'm just having we covered that the first week, so you've seen this before. So you can see that the reason refrigeration works so well, it's really more of an A parameter. It's due to the positive interactions that gas molecules have with each other, which is why that works. Anyway, okay, so with that said, we're done with Joule-Thomson stuff, and now we're getting on to chapter 4. By the way, by tomorrow, I'm going to have a major revision of the book, basically chapter 4. So we're now on chapter 4. I really need to revise it, and I'm mostly done on chapter 4. Just for readability, I don't think there's many technical errors, but it's just not very readable because it's a second draft. So anyway, chapter 4 will be mostly updated by tomorrow, so look out for that. I'm barely kind of ahead. And we are on chapter 4. Again, the equations are all fine. It's just I'm trying to make it as readable as possible because I think this could be reasonably hard, especially if we get into entropy. So we're getting into entropy now. And to introduce entropy, and because we have an exam coming up and thermodynamic proofs tend to be the things that really get people, let me do some thermodynamic proofs. And let me do some exact versus inexact. Now, remember that exact differentials are like internal energy and enthalpy. They're path independent, and that's why, remember that I can always, whenever I have a change of internal energy, for example, CV dt, it works for everything. Isothermal, dt is 0. All isothermals have change in U of 0. If I ask an isothermal question, write delta U is 0. It's automatically correct. Okay, but if it's adiabatic, then du is CV dt. I just said the same thing twice because it's exact. The same equation for the change in U should always work. Okay, inexact is like work. Remember, there's two different types of work, reversible, irreversible. I showed you graphically how irreversible is always the, reversible is the greatest negative. They're different. Reversible is the greatest negative. It's path dependent. I also did a really kind of a complicated derivation, doing a little pass and showing you how x dy is path dependent. Anyway, we've done all this. But now, this is going to come up over and over and over and over and over again, so let's just do some examples. Why not? Recall that I had this thing called the Euler Test. Euler Test, which is that if a differential is exact, it can be you can take derivatives in any order and they should give the same result. And let me just show you. I don't want to write down the formula because I'm kind of talking too slowly today. Let me apply it. Let me apply it to change in U. Now again, I told you that the change in work was inexact, and we did it graphically. We did it a bunch of ways. I told you to trust me that heat was inexact. I'm actually going to prove that in a bit. And I told you that heat and work, both being inexact, sum into the change in U, which is exact, but I never proved it. I just told you that and you accepted it. So for the heck of it, let me prove it. And to prove that the change in U, the differential of U, is exact, I'm going to use the Euler Test. And the Euler Test, let me remind you, I'm just going to arbitrarily pick change in U, change in V, and let's do constant T, just like we did just a minute ago. Change in U. Now again, if I, what the heck is wrong with me? Sorry, there's rules to this, right? So if I held T constant, now I need to let it change. Okay, there we go. Now, the Euler test says that the change in, what is this? Okay, so just remind you of that. Euler's test says that if I take the change in U with respect to V at constant T, and whatever the heck that is, if I take that thing and look at the change in T at constant V, then it's the same thing if I permute them. So I did change in U, change in V, so I'm going to do change in U, change in T at constant V, and then I permute that change in V at constant T. Yeah, I know, it's kind of like X, Y, Z, 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 X, Y, 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 X, Y, Z, right? It's like my password on my phone, 1001001, so it's a random series of zeros and ones. No one ever gets it. I bet there are people out there like that. So anyway, let me see. U, T, T, V. V, T, T, V. Okay, there we go. T and V, then V and T. V and T, T. Okay, so I got that right.
What happened to the third term? There's three terms on the top, and then we went down to 2.
No, there's only 2. No, there's only 2 terms. I'm just pointing out that du dt is CV. No. Changing U. No, it's just 2 terms. I could add more terms. We actually will do that in chapter 6, by the way. We'll start letting moles change. Right now, we're just doing T and V. There's only 2 terms. What I screwed up. I think just label sounds.
Yeah, I was going to say, yeah. I think that's where he thinks it's 2 terms, is that look like minus. Yeah.
Sine equals sines, yeah. Now, actually, no, you got to look out for this in the book. A lot of people get this, or on the exam. If I do something like this, sometimes people see this. Now, don't write this down, all right? I don't want you to see that. But sometimes people, if I do something like this, people sometimes say dt is equal to this. See what I mean? If I write something like this on the exam, sometimes people say, oh, well, dt is du dt. No. Just look at the whole thing. Change and use this, all right, but then cd. That is that. There we go. Okay, so now the reason I need to write this down is that it helps me do the Euler test. That's why I need that. Okay, now in fact it lets me do this. And this is very important. Okay, the change in U with T at constant V, remember at constant volume there's no work, and that means the change in U is heat. And that makes it heat and the change, anyway, I'm very stupidly trying to stammer out that this is CV, just like I wrote up here. Right? Here, okay. Now, if this is CV, what you do is it just, now this is kind of almost childish, but anyway, it needs to be said. If this is CV, it just hops on top, essentially, in case you get a little confused what to do with the symbology. This is CV, so you just plop it up on top. So I'm now doing the change in CV with respect to volume at constant temperature. Now, do you remember how I told you how heat capacity changes with temperature? Remember that? It was a long time ago. Maybe don't even write this down, but I was showing how heat capacity changes with temperature, and I talked about how you unfreeze like rotations and translations, and you level off, and this is about room temperature. But then vibrations kick in, and then you remember that? Yeah, it was a while ago. Remember, this is a rotation, translations, then rotations, and then this is about room temperature. But then vibrations kick in a little higher. Okay, if temperature is constant, what do you think this is?
0.
Right, this is 0. Right? Yeah, there's no reason to think that CV changes. If temperature is constant, then we're just, let's say we're stuck here at room temperature. Well, there's the value of heat capacity. It's not changing. There was no reason to change with volume, right? So that's 0. Okay, now let's do this stuff. Okay, now I happen to know that this, let's see, what have I got here? DVT. I am blanking out, unfortunately, on what to do with this. I swear to God, I had this straight a little while ago. Changing U. Wait. What's the change? God, I'm being an idiot. Yeah, 0. Changing U at constant temperature. Now again, I'm doing perfect gas. Changing U with volume at constant temperature. Change it to, that's not O, that's not oxygen, that's 0. There we go. Sorry, I'll be exact here. Changing nothing with temperature is still nothing. Okay, there we go. All right, so now 0 equals 0 counts. That works. So that's a pass of the Euler test. And so the change in U is exact. Anyway, this is just an example of a thermoderivation of Euler's test. Euler's test is hugely important. I know I introduced it on the second Extra Friday. You probably forgot about it, but here it is. Just permute the order of differentiation and set it equal to its, that, and go. All right, and you're going to need to write. Let's just do another example. Let's do another example to make this more clear. And let's do the change in heat. And I'll put that. I'll leave this up here, and I'll just do that here. Let's do change in heat. So this is exact. Let's do heat, which is inexact. So now again, what I'm going to prove to you is that the change in heat is an inexact differential. U was exact because it passed the Euler's test. Heat is inexact, it will fail the Euler's test. But now to do this, I'm going to have to, because I'm going way too slow, let me just point out, I'm just going to do some algebra and isolate heat on one side because I need to do that. Changing U minus the change in work. Okay. Now I happen to know that I'm going to want to change it, still changing heat. I'm going to want to do change in U. You see what I'm kind of missing here is I need to have a d blah. So I'm going to want to put that as CV dt and work. Of course, I'm going to make that minus work, and let's do this reversibly. So that's going to be plus PdV. Minus work, right? Work is minus PdV. Minus work is then plus PdV. Okay, well, the reason I want to do that is I want to remind you of this, the f dx, constant y dx. I probably should have put this up earlier, so sorry about that. Again, I get a little twisted up on a Friday. I don't think straight because I'm just getting tired. Okay. All right, now actually this is a better example of why you want to do this. So if I ask something like this on the exam, write the change in whatever. God knows what I could ask. Remember, this is the point of why this is kind of a challenging class is I can write the change of anything. I got so many things I could ask the change of. Okay, then of course I'll make it clear how to begin. Your job is then to equate that with the change in a function. And then we can, let's make our lives easier. Okay, f is q, x is t, y is v. Now this is a fifth grader could figure this out. But then a college student needs to recognize that df dx at constant y is the change in heat with respect to t at constant v, which is CV. And that the change in f with respect to y at constant x, of course, is the change in heat with respect to v at constant t, and that is p. There you go. All right, now what? Okay, now Euler's test. And God knows I have boxed myself in real well. I think I'm going to write out Euler's test and then work it on the other side. Again, thank you, small board. Okay, let's do... I'll write this out explicitly because now I have to admit I'm confused. I've got myself a little confused what's what, and if I get totally confused, I know that we're dead. I'm dead. Okay, again, I'm doing change in x, change in y, so now I do change in y, change in x. Again, formulas will be on the cheat sheet. Not that this is particularly all that difficult to remember. There you go.
How do we know that dq over dv at constant t is equal to pressure?
Here?
Yeah.
Because it lines up right here. See that? Q is F, T is X, V is Y. And look what I'm left with, right? Q, V, T, P. There we go. Right, now that's how you keep this straight. Because this is a freaking zoo of letters. You will totally get lost. If maybe, some of your math geniuses, you probably already figured all this out. Great. Collect your A at the door, all right? For those of you who need to go a little slower, this is how you do it. Both of you get the same grade. If both of you get the right answer, one of you just goes to the bar center. So, okay, so now I've written this out. Now again, you've got this on the cheat sheet. Now you just substitute in your letters. And let's do this side first. Okay, so this is change in heat with respect to, damn it, you see, I've got myself, F is, you see what I did? It was, anyway, I was being stupid. X is T at constant V. Okay, all right, so let's do that. And I have to work that over here because, again, I bought myself a good corner. Now, remember, we're going to show that these are not equal because heat is inexact. Okay, what do I do there? All right, so, okay, let me remind you. I'll rewrite it over here. I'll rewrite it. So, V, heat. So I'm working the thing, but I'm having to go from right to left, which is awkward. Okay, what do I do? Let's see. This happens to be, I do something a little slick here. The change in heat at constant volume, this thing, you know what that is? CV. You recognize that? Oh, here, I'll be very careful how I do my symbology. See that? The change in heat at constant volume is CV dt, so CV dt is CV. Yeah? You follow me along? Yeah, it's in the book. Anyway, so this guy CV is because we're at constant volume, and it's literally the definition of CV. And what's this? Right. I just did that. I just did that a minute ago. That was part of the last derivation. So hopefully you remember that. Okay, now let's work the other side. Okay, and that's dt. Change in heat with respect to volume, constant T, constant and equal. I need to put a question mark over that. All right, now I have to go over here. Okay. If all of this is a P, and again, I'll try to get my symbology, hopefully you'll follow along here. If all of this is a P, it hops on top. It hops on top, and then I'm at constant volume. dP dt at constant V, if I'm going to use the perfect gas law, or even if I use van der Waals, it wouldn't matter. Let's see, this is NR over D. Okay. Those are not equal. No, not equal. Now remember, it's not that there's, in case you've gotten a little cross-eyed, it's not that they're not equal because I didn't use the van der Waals. It's nothing like that. They're not equal. That means that heat, the differential of heat, is inexact and path dependent. Also recall that those paths are reversible and irreversible. Not constant pressure, constant volume, which is kind of weird, but it's a reversible, irreversible. Reversible, reversible, irreversible. That's right. So anyway, I've kind of stammered too long on that, so let's just move on from there. Okay, so heat is inexact. Okay, now the point of this is that I'm actually introducing entropy. And I don't know where the formula for entropy came from, and I tried looking it up. I think literally someone just thought of it, and that would probably be Carnot. Sadie Carnot. Somebody figures out that there's this other thermodynamic variable that's really the most important, and they figure out that the damnedest thing is So we're going to go in a different direction, by the way. It's the change in heat over temperature. Change in heat over temperature. Someone just says, hey, I'm going to stop thinking about heat. I'm going to start thinking about heat when I divide by temperature. And when they did that, they found something that seemed to be in charge of almost everything. And it turns out that this is entropy, which is S. Now, if something is important to thermodynamics, it's a state variable. If it's a state variable, it's exact. So, let's see if I magically divide by T, whether the Euler's test will now pass, because before it failed. Okay, to do that, let me do this again. Now, the way I can do, let's do the right-hand side, dDV. Now, the change in heat over temperature, change in T, constant V. And again, I'll do the left-hand side in a minute. Okay. Now, it turns out that, okay, what can I do here? What can I do here? Let me see where I'm at. I get a little bit, this actually frightens me a little bit. Okay, change in V with the change in, what this ends up being is CV over T dt. No, sorry. The way I do this is, I think I can do this. I just bring the T down. I can just bring the T down. And this ends up being the change in V, CV over T.
How can you take the t out when you're taking the derivative with respect to t?
Actually, yeah, I think it's because on the exterior, the temperature is constant. Is that right? I think so. Yeah, is that right? Yeah, I think that's why, because I can take it out as a constant. I have to admit, I'm a little perturbed with that right now myself, but I'm pretty sure that's okay. Again, it actually has to do with the fact that temperature is constant. Oh, great. I remember I got flummoxed like this a while ago, and I had to do a lot of video editing, maybe in that situation. But I'm fairly sure that that's okay, because ultimately, the next derivative is a constant t. So I think that's why that's okay. Let me look into that, and I'll let you know next time and correct the video if I flummox this. That's what's in my notes. It's just I'm like you. I'm not believing it right now. So let me just move on, because I don't think I'm going to unstick myself. Let's do the left-hand side. And for completeness, I'll write this out. T, D, V, the change in heat over temperature, constant T, constant V. Okay, and this is actually going to be the change. It's still going to be, you know what? Now hold on. I'm going to go nuts until I figure this out. And I think the way to do that is to write this out. Write the change in heat like I did before. CV E. Okay, you see what I did was I just wrote what I did before. I just divided everything by T. And then I'm going to line that up with F. So I've got a new F. F is now Q over T. Got df dx at constant y dx. You see that, yeah, I should practice what I preach. When I get confused, I should just go back to this. Okay, F is Q over T, X is still T, Y is still V, and now I can see how I get myself unstuck. I see how I get myself unstuck is that, so let me Just, God, I'm sorry, folks. I should have, I told you Fridays are bad days. The X is the change in heat over temperature. X is T at constant V. Okay, the F, dy at constant X is again the change in heat over temperature, constant V at constant T. Okay, there we go. Now then, if I'm questioning whether change in y, change in f with respect to x at constant y at constant x is equal to change in x, change in f with y, constant x, constant y. Is this the case? Okay. Again, sorry, this is me at my worst. What I've got is the change in v in df dx in that, right? So, and that's CV. Yeah, you see why that works? See why that works? Yeah.
I don't see it.
Okay, no, that's fine. Okay, the change in y is the change in v. Let's go slowly, it's okay. Sorry, I kind of blew out a lot of time. Okay, change. Let me just start this here. Okay, dSEX at constant y is dq over t, dt at constant v. This is CV over t. That's what I kind of flies together. Now, you see why that is? You see how I lined these up? Okay, I took the change in heat, I divided everything by t, and then I simply equated that to my change in function. So it allows me to do this. Now, let me do it for the right-hand side. Change in f with respect to y at x is the change in q over t with respect to v at constant t, and that's p over t. Okay, now, Euler's test, change in v, change in heat over temperature with respect to t at constant v, constant t, is now the change in v of cv over t, constant t. That's how it survived. It's because it lines up here. That's why that works. Okay. Now again, now you see why I actually do kind of know this, but I didn't know it as well as I should have. Now that t is constant, remember why I was harping on that? Now that t is constant, I can definitely bring it out. And what is this? Still 0. I'm still trying to change CV at constant t and I can't. It's 0. Okay, that's one side. Let's do the other side. It better also be 0. Q over t, constant v. Okay, this is p over t. So what I'm doing is the change in t of p over t. Okay, p over t is nr over v. nr over v, what's the change in t? There's no t present. 0. Okay. Oh, God. This is the most horrible thing I've ever done. Jesus, look at this. Hey, look, you just saw me get confused. I've been doing this 10 years. I have a textbook on this. You just saw me get flummoxed horribly. And the way I got undone, so maybe this is a good lesson, the way I got undone was practicing what I preach. Write out the change, line it up with df dx, and then write up Euler, and then so that's me lining up all the variables, making sure all my ducks are all lined up. Then I wrote out Euler's test, and it went from there. No problem. Now, I happen to know that this needs to be exact. This is equal to that, and it is. The change in heat over temperature is exact. So there you go. Now that means that the change in heat over temperature is a state variable. That means it has to be something really, really, really important. We have to know what that is. It has to have some other form, something that we're familiar with. And as I stated, it is entropy. So that is, yeah, there you go, that's entropy. Okay, so let me tell you some things about entropy. And we're going to stop with equations here because you see how well that's going. Let me tell you some things about entropy, and maybe we'll get out a little bit early, just a minute or two early. Maybe, yeah, we'll get out maybe 5 minutes early. I'm a little, not now, all right? But now this is chapter 4, and this introduces us to the second law. Okay, the second law. We're in chapter 4 now. And of course, it's all about entropy. Notice I'm writing the change in entropy. I'm writing the change in entropy. I'll tell you what entropy itself is. If entropy, the change in entropy is exact, if ds is an exact differential, then there has to be an equation for S. I've got the change in S is equal, what about S itself? That unfortunately is horrifically complicated when we show it in grad school. I will give you a hint of what it is, but a little bit later. Right now we're going to talk about the change in entropy. Now entropy is so important, it determines everything. Like why the universe exists, why we have a planet, why you're here. Entropy determines all of it via the second law. There really is only one law of thermodynamics as far as I'm concerned, because the second one's the most important. The second one is so complicated, there's actually 2 forms. And this is called the Clausius form, which is you cannot convert all heat into work. Now there is another statement that I'll cover next time, which is that the entropy of the universe is always increasing. That's the one you probably have heard of before. But this is more of the advanced undergrad level. You can't convert all heat to work. It means the same thing as entropy is always increasing. It's just kind of hard to see. I'm going to start with this because this is kind of the neater one. This is the one you probably haven't seen before. And I want to think about what that means. You can't convert all heat to work. Now remember how heat capacity at constant pressure is higher than heat capacity at constant volume? And I said that's because when you input energy into the balloon, it expands. You did work. But then I asked you this. Did all of the heat turn into work? What do you think? Now again, your instincts are right. I have a balloon. It's at room temperature. I input heat. Does it expand to the point where it goes back to room temperature? No, it wouldn't. It wouldn't. It'll just expand. It'll convert some of that heat to work, but not all of it. Okay, so you kind of know that. But of course, we're going to put some equations to all this. Now, there is a way that I like to try to fool people. I like to fool people about this. Talk about isothermal. If we're isothermal, the change in U is 0, and therefore, change in work is minus the change in U. Okay, they're equal and opposite. What? Now hold on, I just said you can't convert all heat to work, but yet I just wrote down a very simple equation that equates them. Minus sign doesn't matter. Those are human things. Nature doesn't know minus signs. Nature doesn't know backwards and forwards. All right? This seems to belie that. But now remember how I keep describing work and heat, especially for isothermal? We'll do a compression. Here's the magic cylinder, and I press on it. I compress it. Does the gas get hot? Yes, it does. Not if it's a Joule. Not unless if it's in a Joule-Thomson experiment, it won't. But let me answer one of the questions on the homework. If the magic cylinder is not the Joule-Thomson thing, right? If I have an enclosed cylinder and I can press on it, the gas can't escape. The gas gets pressurized. The gas gets hot. Okay, so that work, is that positive or negative? I compressed it. Positive or negative? Positive. Positive, right. Okay, but now how do I get the temperature back down? It's isothermal. How do I do that? It's metal, it's a heat transfer. Positive or negative? Negative. Negative. Positive and negative, it cancels out. All right, so you know that. You better be able to do that. I'm going to put that on the test. Guarantee that's on the test. My point being, What did I start with? Did I start with work or heat? Work, that's right. I started with work. I can't convert all work to heat. Sure, that works. It doesn't go the other way. And that's the damnedest thing. Okay, well, so what? Any of you bike to campus? Okay, so one of you bikes to campus. Anyway, good thing. I'm scared of biking on streets because a lot of people get run over that way. Okay, so you converted all your work to heat. The rest of you, did you drive?
Yes.
Heat to, all right, was that work to heat or heat to work?
Heat to work.
If you drive, you burn gasoline, heat to work. Heat to work. Okay, you can turn work to heat riding your bike, and that does function. But for the most part, our modern society isn't based on turning work to heat, it's turning heat to work. Seriously, think about every modern convenience you have. Your car, these lights, which are made in a power plant, which turns heat from nuclear fuel or burning gas to work, which is a turning turbine, turning dynamo. Your car turns heat to work. Now, we do have an ability to turn work to heat, so riding a bike, but we don't do that to go see grandma in New York, right? We turn heat to work. Our big machines are based on turning heat to work. And that sucks, because while I can turn all work to heat, I can't turn all heat to work. And that means that there's a limit on our fuel efficiency, which is actually quite severe. We're gonna calculate that. Next time, 2 sessions from now, right after the test, we're going to find out that there's an equation that fundamentally limits the efficiency of all machines. Okay, now the reason I want to point this out, and then we're going to end there, is that the reason that work and heat are not equivalent, remember I told you that work is understandable to me as the outsider. I see the piston closing in on the gas, and those gas molecules get hit. But I ask you this, if those gas molecules are buzzing around, is there any moment in time where those gas molecules simultaneously all move in the same direction and push the piston backward? Does that ever happen? No. Entropy is a one-way street. Engine efficiency, heat to work is a one-way street. I can do work and get those gas molecules moving, but here's what happens. Let's do what and how fast. I looked this up on, well, I just know this stuff because I'm a physical chemist. Okay, if I do work on gas molecules, within a certain amount of time, those gases, here's the piston, here's the gas molecules, right? For a brief moment, it's coherent. They're moving around, but bammo, they got put in a direction. How fast does it take them to become randomized? How fast do you think that is?
1 femtosecond.
That's actually very close. 1 nanosecond. That's fairly close. 1 nanosecond it takes. And if you're in a liquid state, it's kind of hard to think about doing work in a liquid state. It's actually faster. You can't beat this. In a solid state, it's even faster. This is actually the second law. This is where this comes from. Because what I understand, what I perceive as work, is only perceptible to me. It's turned into heat, which is incoherent motion, so fast. Your ability to discern things is about 1 millisecond, 1 times 10 to the minus 3. So work is turned into heat, essentially, 1 million times faster than you can even perceive it. Now, the dangerous thing is, you know it never goes backward. The heat never turns into work. Because, again, this is a one-way street, and you know that because of how fast it happens. So just like you can't, as I used this analogy before, you pop a kernel, but you can't put the kernel in the refrigerator and have it go backward, right? So there you go. Well, with that, I think I've talked long enough. Next time, I'll have all your homeworks, and we're going to cover entropy, how to calculate entropy.